Today, we're going to be talking about implicit differentiation. And in order to do this, we have to set the stage for what we're going to do. So we need to start thinking of d dx as an operator. So let's think about the derivative of s using Lagrange's notation of f. That's going to be f prime. This is useful when we're dealing with functions that have a single variable. So for example, if we know that f of x is x cubed plus 2x, we can quickly find the derivative f prime of x by using the power rule 3x squared plus 2. But sometimes we're not going to get something that has all our x's grouped nicely together on one side. So here's how we're going to deal with it. D dx is now going to serve as an operator, just like adding and subtracting, but this one indicates differentiating, specifically with respect to x. In other words, we're going to treat x as the variable that we're differentiating with respect to. So x is the variable we're focusing on, just like we did over here. We focused on the variable x. This is useful when we are finding the derivative of something that doesn't have an x in it. So here's an example of finding the derivative of something that doesn't have an x in it. We can think about d dx as an operator, and if we're finding the derivative of y, we can put that over 1 and go across the top dy and across the bottom dx. So dy dx is how we write the derivative of something that doesn't have an x in it. So let's use the chain rule to help us think about it. Remember, the chain rule has an outer function. So our outer function is u squared. And then our inner function, that bubblegum, is going to be y itself. So our outer function is u squared. We're using y as our variable, so we're going to write that as 2y. And then our inner function, you can think of us as finding the derivative of, so d dx of y. And we just learned up here that when we're finding d dx of y, we can write this as dy dx. Therefore, the chain rule helps us see that the derivative is 2y, that's the candy shell, and then dy dx is the derivative of the inner. So essentially, anytime we're finding d dx of something that doesn't have an x in it, so think the letter t, we can write this as dt dx. So this is helpful because we can use this to find the derivative of implicit equations. Notice the explicit equations over here, all the x's are gathered together on one side of the equation. These implicitly written equations are all mixed together. There's some x's and y's over here. There's some x's and y's over here and x's and y's over here. So when it's not useful to get y by itself on one side, we can use implicit differentiation. We're going to start real simple. Here, we're finding d dx. That means we're finding the derivative, and x is our variable of this. So we know how to do this. We're going to use the power rule. We're going to say this is 3x squared. But here, we're going to find the derivative where x is our variable. But the problem is we don't have an x in there. So let's think about this with the chain rule. The outer function is 3y squared, and then the inner function is y. How do we write the derivative of y? We write it as d dx of y. Wait, we just learned another way to rewrite that. Instead of d dx of y, we're going to start writing dy dx. So anytime you need to find the derivative of a variable other than x, you're going to write it as dy dx. Let's try it again. Here we've got the addition rule. So the derivative of x is just 1. And then the derivative of y is also going to be 1, except we're finding the derivative of something that isn't x. So we're going to add a dy dx on the end to it. That shows us we're finding the derivative of y, even though our variable of focus is x. Let's try this next one with the quotient rule. We're going to do the second function times the derivative of the first, plus the first function times the derivative of the second. For the second function, I want you to think about chain rule. The outer function, the derivative is 2y, and then the inner function, that y, has a derivative of dy dx. I don't know why I wrote that so high up. Oh, because underneath I want to rewrite that as y squared plus 2xy dy dx. There we go. So again, when finding d dx of an expression containing y, think about the chain rule. You can find the derivative of whatever the y function is. If you're given 3y to the 5th power, you can find the derivative and get 15y to the 4th power. But then the chain rule tells us to find the derivative of the inside, and that's always going to be dy dx. So again, if we're working with y instead of x, we use dy dx. We think about the chain rule. So here are the steps for implicit differentiation. They may not make sense until we put it into practice, but we'll get it with some examples here in a minute. So what we're going to do is we're going to differentiate both sides of the equation with respect to x. And that notation for that is d dx. We're going to do that on both sides. We're going to collect all terms that have a dy dx on one side of the equation and move everything to the other side. Then we're going to factor out a dy dx, and then we're going to solve for dy dx. That sounds really crazy, but let's do it. Everything's going to be okay. So what we're doing here is we're going to take the derivative of both sides of this equation. Now remember, since we're finding the derivative with respect to x, anytime we see a variable that's not x, in other words, every time we see a y, here, here, and here, we're going to put a dy dx after our answers. This means that we're finding the derivative of y. We're finding d dx of whatever y is there, and we write that as dy dx. All right, here we go. So here the derivative, the outer is 3y squared, and then the inner is dy dx. Plus, the outer is 2y, and then the inner is dy dx. Minus the outer is 5, and then the inner, dy dx. Minus, and here we have an x on our hands, so we can just derive minus 2x equals 0, because the derivative of -4 is just 0. So now we're going to get everything with dy dx on one side of the equation. So I'm going to do 2 steps in one. If it's okay with you, well, you're watching a video, so I hope it's okay. I'm going to factor dy dx out of all 3 of these guys. So I'm going to write this as dy dx, and then inside the parentheses, sorry, I shouldn't have put an equals. Inside the parentheses, I'm going to put 3y squared plus 2y minus 5. And then this 2x right here, I'm going to go ahead and bring it on the other side and make it a positive 2x. So here we've done 2 steps in one. We've gotten all the dy dx's on one side of the equation, and we moved all the other terms to the right side, and we factored out a dy dx. So we're actually almost done. Our goal now is to solve for dy dx. Notice that all of this stuff next to it is connected with multiplication. So we divide it by everything that does not contain dy dx. So we're going to divide both sides by this 3y squared plus 2y minus 5. So our final answer is going to be dy dx equals 2x on top over 3y squared plus 2y minus 5. And we did it. We found the derivative. What's different here is when you found the derivative in the past, it always just had an x in it. Now it's got an x and a y in it, and that's okay. It's still the derivative, and we'll work on using it in just a little bit. Let's try another one. Let's consider this equation x squared plus 4y squared equals 4. So we're going to sketch a graph of this relation here. So if you want to use your calculator to do that, I don't blame you. We're going to get an elliptical shape like this. It should be a little more curved than that. I did my best. So let's find dy dx for the equation. That means we're going to find the derivative of all the things. So here we're going to find the derivative of x squared. That's 2x. Now we're going to find the derivative of 4y squared. So find the derivative of the outer. That's 8y. And then the derivative of y itself is always going to be dy dx equals 0. So now we can start working to solve for dy dx. We can subtract 2x from both sides, so 8y dy dx equals negative 2x. And then divide both sides by 8y, and we will have that dy dx is equal to negative 2x over 8y, and you can simplify that to negative x over 4y. So that is our derivative. Now remember, it's been a little while since we've talked about this, but a derivative is the slope of the tangent line at a given point. So this is asking for the slope of the tangent line at square root 2, comma, negative 1 over square root 2. So if we think about where that would be, square root 2, negative 1, square root 2, I don't remember exactly what it is. It's somewhere around here. So we're looking for the slope of that tangent line right there. So how do we do it? Well, the good news is we know the derivative of this function. We know the slope of the tangent line. It's going to be negative x over 4y. Well, we are required to find the derivative using an x and y, and the good news is it's given to us. So we're going to evaluate this, letting x be root 2 and letting y be negative 1 over root 2. So let's plug them in. We can write this as negative root 2 over 4 times negative 1 over root 2. We're going to clean that up a little bit. That's the same thing as negative root 2 over negative 4 over root 2. When we divide by a fraction, we multiply by the reciprocal. In other words, keep change flips. So negative root 2 times root 2 over negative 4. And at this point, I should have just dropped the negatives. When you have a negative over a negative, that's a positive. So what's square root of 2 times square root of 2? That's 2 over 4, which equals 1/2. And what does that tell us? That tells us the slope of this line is 1/2. So we did it. All right. How do we write the equation of the tangent line? Well, this part's pretty actually easy because we know point slope form y minus y1 equals our slope times x minus x1. And we have all that information. Here's our x1 and our y1, and we just found our slope in the last problem. So we're going to have y minus y1, so plus 1 over root 2, equals our slope of 1/2 times x minus root 2. So now it says write the original equation explicitly and use your graphing calculator to verify the graph. Then take its derivative and compare the result with part B. So what does it mean to write the original equation explicitly? It means to get all your y's on one side and all your x's on the other side. So let's do it. We've got x squared plus 4y squared equals 4. So let's work towards getting all our y's on one side. Let's subtract x squares from both sides. So 4y squared equals negative x squared plus 4. Divide both sides by 4. Y squared equals negative x squared plus 4 all over 4. And then we're going to take the square root of both sides. So y equals plus minus the square root of negative x squared plus 4 all over 4. And to make our lives easier for when we differentiate, we can write this using a rational exponent instead of a radical. So negative x squared plus 4 all over 4 to the 1/2 power. So part A says verify your graph from part A. If you put this in the calculator, it will match the graph that we got in part A. So now let's differentiate. We don't have to use implicit differentiation because that x is by itself. So instead, let's use the chain rule. So dy dx is going to be equal to, let's do the outer part first. So the outer part tells us to use that power, bring it down. So we're going to have 1/2 negative x squared plus 4 all over 4 to the negative 1/2. And then let's find the derivative of the inner. The derivative of the inner function, that negative x squared, is going to be negative 2x. So because we had a plus or minus out front, oh, I didn't write it down. I should have written it down. dy dx. We had a plus or minus out front. We don't really have to worry about this minus sign over here because it's taken care of by the plus or minus. So it's kind of redundant to have a sign here when both are going to be relevant. So let's combine like terms a little bit. Let's multiply these together. That's not combining like terms. We're just multiplying. So plus minus 1/2 times 2 is just x. So we're going to have x times negative x squared. Let me erase that line. Plus 4 all over 4 to the negative 1/2 power. And just for funsies, let's think about different ways you might see this. You might see, because this is a negative exponent, you might see plus or minus x all over negative x squared plus 4 all over 4 to the positive 1/2. And you might even see it using that radical again. So plus or minus x over the square root of negative x squared plus 4 all over 4. So again, remember, I'm cool with this, but you might see it in a different format. So remember, when you have a negative exponent, it goes to the denominator. And when you have a fractional exponent, it makes it a radical. All right, last problem. We're going to find the slope of the graph at the point 3,1. So just to get a visual, the point 3,1 is right here. We're going to find the slope of the tangent line. So we're going to find the derivative. We're going to find dy dx. And then when we do, we're going to substitute in the point we're given, 3,1. So let's do it. So on the left side, we're going to start with the left side of this guy. We're going to use the chain rule. There's that outer function of 3u squared. So think we've got 3u squared. How do we find the derivative? That's going to be 6. We're going to leave our bubble gum alone for this part. And then that's to the first power. Now we're going to multiply by the inner. So we're not worried about the outer. We're going to find the derivative of the inner now. So the derivative of the inner is going to be 2x plus, and then we're finding the derivative with respect to x of something with a y. So remember, anytime you do that, you're going to put a dy dx. So that's going to be 2y, that's the outer, and then the inner is just a plain y, so the derivative is dy dx. So that's going to be our left side. Then on the right side, we've got to use the product rule. So we're going to take that 100 out. We're going to do the second times the derivative of the first, which is just 1, plus the first times the derivative of the second. The derivative of y is dy dx. And now we're going to, well, we could clean up, but honestly, it would make our lives easier to just go ahead and substitute in 3,1. So let's substitute. Everywhere we see an x, we're going to put a 3. Everywhere we see a 1, we're going to put, or everywhere we see a y, we'll put a 1. And our job is to figure out the derivative. So our goal is to solve for dy dx. So let's do it. We're going to have 6 times 3 squared. So I'm going to put 9 plus 1 squared. I'm going to put 1 times 2 times x is 6 plus 2 times y is 2 dy dx equals 100 times y times 1 is 1 plus 3 dy dx. So our goal is to keep cleaning up until we can get dy dx alone. So here, this is going to be 6 times 9. So, oh, just kidding, 6 times 10. So that's 60 times 6 plus 2 dy dx. And over here, we're going to have 100 plus 300 dy dx. Then we're going to distribute that 60 through 360 plus 120 dy dx equals 100 plus 300 dy dx. So now we're going to get all our constants on one side and our dy dx is on the other side. So I'm going to start by subtracting 100 from both sides. And I'm going to have 260 plus 120 dy dx equals 300 dy dx. And now we can subtract 120 dy dx from both sides. So 260 sorry, there we go. So 260 equals 180 dy dx. And then finally, we're going to divide both sides by 180. So I'm going to cut off those zeros, get 26 over 18 equals dy dx, and then simplify a little bit more. That's going to give us 13 over 9. So dy dx is 13 over 9. Now, what the heck does that mean? That means that the slope right there at the point that we plugged in is 13 over 9.